Hello, everyone. Group number one, work was concerned about the interaction between cosmic rays and interstellar dust grains. So first of all, what are cosmic rays?
Yeah.
Sure.
Yeah.
Try, because it's not working.
Yeah.
Okay.
Yeah.
Yeah. Okay. Great. Okay, so cosmic rays. Cosmic rays are basically charged relativistic particles. Mostly, for most part, it's proton, and 89%, 10% of helium nuclei, and a minority, 1% of heavier nuclei. Now, that 1% may seem small, but those heavy ions are actually very important when it comes to depositing energy into matter in the ISM. So where do these cosmic rays come from? Mostly super high energy astrophysical processes, so like supernovae, pulsars, AGN jets, gamma ray bursts. So these are basically high energy particles. As you can see from the spectral distribution, the flux of cosmic rays is still quite predominant, even at the JEV range. Yeah, so basically at these energies, these cosmic rays can penetrate into optically thick interstellar clouds and interact with dust grains in an environment where UV photons would not normally reach. So now, what are interstellar dust grains? These are basically solid particles, size comprised between 0.01 and 0.5 microns. They're constituted of a carbonaceous core, and at least in the dense phase, they're coated by an icy envelope. In our project, we just focus on the core, so there is no ice mantle or envelope. Now, these grains have important astrophysical implication in the ISM. They're catalyst for molecular formation. They reprocess UV, and for what concerns us the most, they are destroyed by cosmic rays, of course. So what we did in our work, we model how how these particles, these grains are affected by cosmic rays, mostly the time it takes for them to be destructed. And in the end, we also model the ionization of the ISM by cosmic rays.
Thanks. Yes, so we used SHRIM, stopping and range of ions in the matter. This is a Windows program, only runs in Windows, and you can generate this stopping power of the targets. So for different elements, I think we did from hydrogen to iron, because that's the heaviest. And then we have this stopping, the SE is basically the stopping power minus d by dx, and the target density was 1.2 grams per centimeter cube. And then we had our target as amorphous hydrogenated carbon, 1:1 ratio. And yeah, so this is the destruction rate. You can see all the signs. It's important to know the unit device. So this is the cross-section. Alpha and beta come from basically from the lab experiment. So they have some sort of errors also. Yeah, and then F of C is the cosmic ray abundance. This is plotted here relative to hydrogen. And then this is a flux. So this is calculated using this energy per nucleon, and then the E naught is the initial energy. Later, Gio will explain. This is the unit, very complex units per centimeter square per second per steradian per MeV per nucleon. And yeah, so I will pass the mic to.
And here we calculated the stopping power, which is the average energy loss per unit distance for the particles as they pass through the target material that we chose to be composed of hydrogen and carbon. On the left-hand side, you can see without the abundance weighting, which reflects only the intrinsic material properties, not the cosmic rays. And when we weigh them by abundance, the shape is dominated by how common the element is. So we see at the top, we have hydrogen than helium. And for the cross-section, it relates to the stopping power linearly. It correlates with dE over dx because more energy loss can imply more frequent interactions. And this is calculated for all elements. And then the flux, it's the number of cosmic ray particles that pass through the target. Of course, units per time per energy per unit solid angle. And here we can see that the abundant elements like hydrogen, helium, carbon, and oxygen dominate the flux. This is at a particular E0, which was in the denominator of the equations that my colleague showed you. So because it was in the denominator, higher energy or higher A0 points correlates to lower fluxes. And this is plotted for hydrogen with different E0 points.
And then we can, this is the laser, all right. I can take the laser. So we will then, spoilers. So we will then introduce the cosmic ray ionization rate, which is basically a very, again, complicated equation, but I want to focus on a couple of factors here, which is this eta, which means that when the cosmic rays propagate into the medium, we have also secondary cosmic ray ionization rays that they are produced by this medium. And then you have a couple of factors here, which is the atomic number and the fractional abundance, and then some cross sections, new ones now that they are computed based on the target that you have bombarded basically with those cosmic rays. And we, 2 minutes. So we have calculated some of those factors. So this is the diffraction time that you saw in the first equation, and this is the cosmic ray ionization rate times this time, and then we have confirmed basically some of the facts that we already know. So they are inversely proportional. So you can see that despite the fact that one goes up and the other one goes up, the axes are inverted. So one goes up, the other one goes down. We also know by the literature standard value, I don't know about the standard value nowadays, but the cosmic ray ionization rate, at least we are measuring, is something approximately 10 to the minus 17 to 10 to the minus 16 to the minus 1, which is something that is somewhere in this regime here, so between the dense and diffuse cloud. And then we have the lifetime of a typical molecular cloud, which is approximately 10 to 50 million years, which means that if you bombard this molecular cloud with too many cosmic ray ionization rates, then all of the material inside this cloud will basically dissociate and you will not have a molecular cloud anymore. So this is something that we see here. So this is a dense cloud with a cosmic ray ionization rate approximately 3 to 10 to the minus 17. And this is a diffuse cloud that the energy is higher, the cosmic rays are higher, and they can propagate into the molecular cloud better. So some of the conclusions that we derived based on this experiment is basically that depending on the cross-section that you saw, which was alpha, sigma to beta, blah, 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 depending on that beta, this cross-section can change, and this whole idea of the chemical evolution inside the molecular cloud can also change, which means that some of the things that we discussed and we observed in this one might not stand if you have a different correlation between the cross-section and some of the beta factors. And then we have calculated some of the things that you saw also in the figure, which means that we have something around 10 to 400 million years with a cosmic ray ionization rate somewhere in between these two factors, which means that it's good, we can have molecular clouds. And then we can say also that for the model that at least we explored, 90% of the contribution to the diffraction of these elements came from hydrogen and helium, and approximately 10% came from the remaining of the elements. And this is basically what you can observe here, that the cosmic rays, as they propagate into the cloud, they attenuate, so you have less and less and less cosmic ray ionization rate as you progress through the cloud. That's it. Thank you.
Other questions?
Because we are interested in the low energy cosmic ray ionization rates. Those are the ones that penetrate into those clouds. So we were interested, if we go back to this figure, we are interested into this cosmic ray ionization rates, not those ones. They have very small cross-section, so they're basically not negligible, but you know. those do the damage.
More questions? What a bit. Yeah. Okay. So maybe group 2 can get ready. So let's thank again group 1. Yeah, thanks.
Okay, hi everybody. This is group 3. So this is tracing the physical properties of warm molecular gas through observation and models of the submillimeter CO rotation ladder. And this is the group, which we don't have time to explain, but we did number everybody, so you know who everybody is. So to introduce our target is the Orion bar PDR, as seen here in this image with Hubble in the visible. So the Orion bar PDR sits at around a distance of 414 parsecs. So this is within the Milky Way, and this sits at about a metallicity of Z solar. And so you can see here, this is what it looks like in the visible. But if we go to longer wavelengths in the infrared with something like JWST or Herschel, we can see a lot of the gas structure and the interplay between the gas and the dust and the heating mechanisms. So the goal of this project was to characterize the physical conditions of the Orion bar PDR, which is a local template for dense and highly irradiated PDRs in general. But before we get started, what is a PDR, or a photodissociation region? So PDRs are characterized anywhere where far UV photons dominate the heating and the chemistry in the region. So this can happen all throughout the galaxy and across the universe. But the one that we're going to be talking about today is between an H2 region and a molecular cloud. So you can see here that we span a range of AV, and we also span a range of gas temperature as well as density. You can see here in the deepest parts of the PDR, where the molecular cloud is, we have CO, and we can use CO as a tracer of the temperature, which is something we'll talk about next.
The data that we used in this hands-on project comes from the Guaranteed Time Key Program Hexos, which used the HiFi instrument of Herschel Space Telescope. It aims at doing a molecular line spectroscopy with a high resolution. So in this work, we studied spectrum, that is a line survey that targeted broad bandwidth going from 490 to 1060 gigahertz in order to observe CO rotational emission lines. And indeed, in these spectrums, you can find lines emitted by rotational transition of CO molecules, as well as 13CO and C18O. And you will see why we study this.
So we analyzed the HiFi data and fitted the observed with using GILDAS and class, and we used Gaussians to fit the observed lines. And our target was to derive rotational temperatures and total column densities using these rotational diagrams. How did we do that? The level populations follow a Boltzmann distribution. So we expect to see straight lines, as you see here, and that's what we observed. And once we fit a slope using the second formula, we get the rotation temperatures. From the intercept and the partition function, we can derive the total column densities. And here here we can see that carbon monoxide had really high temperatures in comparison to its isotopologues C13CO and C18O. That's because the isotopologues and CO trace different physical depths in the PDR, and we saw a similar trend in the total column densities. And we must remember that here we are assuming local thermodynamic equilibrium regime.
So now we move away from the assumption that we are in LTE, and we do non-LTE modeling with the escape probability code radix. For example, we take the CO transition J is equal to 2 to 1. As you can see here, we have plotted line opacity versus the column density of CO at a constant gas density of 10 to the power 3 per centimeter cube. The line opacity increases with the column density, and this is because the line opacity depends on the population of the upper level, which is related to the total column density by the Boltzmann equation. We also see that at high gas temperatures or high T kinetic, the line opacity is less. And this is because higher levels are populated at higher gas temperatures. And so the population of the N equal to 2 level decreases. Next, we plot the Rayleigh Jeans temperature or the brightness temperature with respect to the total column density. And we see that the brightness temperature increases with column density in the optically thin regime. And this is because when you have more CO, you have more emission and more intensity. However, in the optically thick regime, we see that the Rayleigh Jeans temperature saturates. And this is because the photons in the medium are reabsorbed and not emitted. We also see that this temperature saturates at the value of T excitation, which is less than T kinetic, as you can see from the plot here. And this is because we are still in the non-LTE regime.
Finally, we look into the PDR code model made by the medium PDR model with physical conditions of Orion bar. So this we see the evolution of hydrogen number density with increasing visual extinction, or as we see deeper into the PDR. And what we see is the transition of atomic hydrogen to molecular hydrogen, and the gas temperature decrease with this transition. And this is the transition of carbon from ionized carbon to atomic carbon to CO as the visual extinction increase. And this happens around 0.5 to 1 AV.
So, in conclusion, from the estimated column density ratio between 12 CO and 13 CO of about 4, which is lower than isotopic ratio value in our Arion, we can infer that for 12 CO emission is optical thick. Instead, between 13 CO and C18O of about 7, which is similar of the isotopic ratio value in Orion, we can infer that for the both molecules, the emission is optical thin. Furthermore, from the Radex models, we could estimate the gas physical condition from the CO at that observed frequency range. And we could suggest that the gas is warm and dense in Orion bar. Therefore, CO ladder is an excellent tracer of warm and dense gas in high mass star-forming regions. Finally, we would like to thank our tutors and the organizers of this school for giving us this opportunity. Thank you.
Questions?
Come on.
Come on, come on.
No.
Come on.
What? I can't see. Oh, there's no one. Okay. So just a question. So we know very well the structure of the Orion bar. So is there a large velocity gradient in this region? So is the LVG hypothesis justified?
Yeah, we actually didn't do the LGV gradient in the Radex models. We just did I think it was the original. We didn't actually look into that. That wasn't something that we did. But it probably would be a good approximation in Orion.
Mm-hmm. Oh, sorry.
Thank you. How did you have any results from the literature that you could compare yours with, and how did they compare?
Yeah, so on this this slide right here, where we have the do you want to? Okay, yeah. Yeah, for these values right here, the 70 and 7, these are actually literature values that we would expect from theory. And then we find in the actual observes, when we actually do the modeling, we find lower values for 12CO, but a similar ratio for 13 and C18O.
Okay, thank you.
Yeah, thank you. The group talk that you all waited for, where we will talk about dust SED fitting, and we were supervised by Frederick and Annie. So why you should care about dust? Well, I think this is a slide that I kind of almost stole from Javier. So you might remember that he had like this slide where he said that half of the bolometric luminosity of the universe is in the dust. And this is here an example that I took from this paper there, where you have some luminosity, or maybe it's basically arbitrary unit, and plotted that against the wavelengths. And you see that the starlight gets reprocessed, absorbed by the dust, and then re-emitted in the far infrared. And you can use this to do many nice things. So for example, if you look at this problem that has been observed with Hubble, you see that there's like some protostar in the right, and you might want to know, okay, what's like the mass reservoir from which this star could draw. And you can use, for example, also here, Herschel, to use the flux at the different wavelengths to do an easy modified blackbody fit to infer the dust mass and temperature, and then you have an idea about what this is. And this, of course, also works for galaxies. And what a modified blackbody is, this will do my colleague.
Okay, so usually we use modified black body spectrum to simulate the emission, emission continuum of the dust. So it's based on black body spectrum, but with a factor of opacity, and also we need to scale it according to the dust mass. So here you can see the shape of it with a given set of parameters. So as an example, to fitting the observed data. So here, like we give like 5 artificial data points, given with random Gaussian noise, and under the assumption of no correlations parameters located in Gaussian distribution. So we can fit the observation data according to we can give a best fit according to our observation. So, and here you can select how the parameters is in fact the shape of the modified Gaussian, but the modified black body spectrum. And also like understand, because like we know like those parameters can always like sometimes influence with each other. So of course we can give an assumption that the parameters are correlated with each other and generate a series of correlated parameter space, but that's another story due to time limitation. We cannot give a very detailed.
Okay. So yeah, we started off by generating 1,000 realizations of these parameters, but of course, assuming that now, as you could see in the previous plots, because these beta parameter and this temperature parameter are both very good at modifying the slope and the peak of the blackbody spectrum at sort of far infrared wavelengths, they are degenerate. So we want to explore that parameter space, generate 1,000 realizations using these correlation coefficients. Here's a subsample of SEDs that we have. And once again, we generate synthetic in which we add an additive Gaussian noise, which is uncorrelated with the wavelength. When you add a noise to simulate something like a calibration effect. It's using a least squares fitting routine. This is a locally explore parameter space rather than going through a full range of parameters that you might think are physically reasonable. And then we can compute the uncertainties on these best fit parameters and explore the distribution of these. And my colleague is going to tell you about that.
Yeah, so here, if we go back to 1,000 points to get the best fit parameters shown in red, this distribution is has a different slope compared to the intrinsic physical distribution of these two parameters. And this distribution matches very well with the posterior distribution of Bayesian inference for a single set of data. So basically, this red distribution is influenced by the noise of the model from the inference. And to get rid of this effect, we probably have to employ hierarchical Bayesian models. And also, we can plot the distribution of the chi-square for all the fits. And we can find that for uncorrelated noise case, this distribution matches really well with the theoretical PDF of the chi-square for degree of freedom of our case, basically 2. But if we have a correlated noise case, basically you imagine you have data from a single field wheel with calibration error, for example. In this case, your chi-square distribution will poke out above this PDF distribution. Basically, it means that you're deviating from this chi-square distribution with this specific degree of freedom. So besides the empirical models, we also tried some physical-driven models like the DAS-EM. Here are the parameters you can change. For example, you can change the radiation field strength. So here, if you increase the strength, your ICD is going to have a higher value, but also the large grain size, the large grains, their temperature will increase. So you can see a peak start to show around the right-hand side of this ICD. So basically, the black body of the large grains start to move towards lower frequencies. And we also changed the grain size by fixing the radiation field. So in this case, larger grains of PAH specifically will lower the ICD at the lower frequency. And the reason for this is that, for example, if you have like really small grains, it has lower probability by getting hit by a photon. So you have time to relax the temperature of the grain toward the CMB temperature. But if you have larger grains, it has higher probability of getting hit by the photons. So eventually you will reach this equilibrium condition of a specific temperature. And if you translate this to the ICD, you will see that for larger and larger grains, you will have ICD that decreases in around the lower, around the higher frequency.
So our next goal is to understand the value of the parameters of the DAS-EM. And in particular, we can use a Bayesian approach to do that. And in order to do that, we remember briefly that the Bayesian approach is formed by a prior distribution and observational data, and all that combined lead to a posterior distribution that describes those parameters. In particular, we have done the Bayesian approach. We tested that on the MBB. That is quite simple because we have an analytical model, but we also done that on the DAS-EM model. And in order to do that, that is a bit more complex because we have a grid of SEDs, and we can sample the posterior with a Metropolis, Hastings, and CMC. And that allows us to understand the values of the parameters of DAS-EM that we can remember are the intensity of the radiation field and the abundance of the different type of grains. And we can also understand their uncertainties. And finally, as a result, we have found that different things, but among them, we can say that we have found that P1, the intensity of the radiation, is anticorrelated with the P4, that is the parameter that describes one of the type of the grains abundance, and also that P4 doesn't really converge very well to a single value as the other parameters do. And yeah, that's it. And yeah, that's it. We would like to thank you all for the attention.
Questions?
You tried to make the fit on which object?
Yeah.
On which object did you try to make?
On an object that has been given to us from our
Yes,
supervisor.
but what kind of object is it?
It's like a galaxy. Yeah.
Synthetic data.
So for the first part, we basically simulated the data by adding the noise. But for the, I'm not sure if you use the Herschel data or.
So I did with the Herschel data, I did just the modified blackbody. I didn't find the time to do it also with DustEM, but there's of course also Spitzer data available, which could be incorporated and so on.
Maybe you said it and I missed it, but the modification of the black body, is it purely phenomenological or is there some physical motivation for this particular shape?
Well, basically the modification is the opacity, that you don't assume that everything is re-radiated equally, but rather you just adjust the slope, and that slope is determined by, the dust distribution, essentially.
Okay, thank you.
Thanks.
Now group forgot, I lost track already. 5, something like that.
Okay, so hi everyone. We did the project on CNO abundance in a nearby galaxy in the wavelength range from UV to optical. And we did it on one galaxy, Markarian 996 right here. It was part of the Classy survey, and it is a dwarf galaxy with known Wolf-Rayet stars, meaning that there are these very, very rare type of stars present that have very, very strong winds. They evolve from very massive stars, and they are just alive for a very short time before they die in a supernova. And we found that this galaxy is a nitrogen-enriched galaxy. So what we did was we investigated carbon, oxygen, and nitrogen abundances. And these are the UV and the optical spectra of the galaxy. And we kind of try to highlight the emission lines and the doublets and triplets and so on that we investigated.
So if we look at the lines that Lynn showed you, we may be interested in, for example, in the collisionally excited lines from some of the metals like oxygen, nitrogen, carbon, etc. Because they help us trace the gas diagnostics, so temperatures and densities. And also there were some nice Palmer recombination lines that help us trace the dust extinction. So to do this, we want to measure the line fluxes and their errors. And to do that, we feed the lines with the LM-Fit package and using single or multiple Gaussian components. And you may think that this was super easy and we did it without problems, but put us to the test. So we thank Zoraida for the line fluxes. And with the line fluxes, we input them into the Python package, which is a very neat package for the analysis of emission lines. As you can see from the right plot, basically PyNeb contains a lot of information on atomic and ionic physics. So it can plot nice Grothian diagrams, and it can measure emissivities of lines based on temperatures and densities, and it can vice versa estimate temperatures and densities based on sensitive line ratios. And so we use this to get gas diagnostics and measure the elements and ions abundances given temperatures and densities that we measured.
Okay, one of the main goal was measure the abundances of our galaxy. And to do that, we use the direct method that consists in compute the abundances using temperature and densities that are measured directly from our data. In each gas, we can always identify 3 or 4 ionization zones that contains different elements that are typical of that zone. That elements can be used to compute all the physical quantities of that zone. So first of all, we had to create our own table of the ionization zone. To do that, before you use PyNab to check how much our elements ratio change with temperature and density. As you can see from our plot, we have elements like O3 that are very sensitive to temperature, but very stable in density. On the other end, there are other elements as C3 that are very stable in temperature, but that are very sensitive to density. And of course, we have also elements that are sensitive both to temperature and density. So we use the most stable elements to compute temperature and density in each zone. That's our table. We use O3 to fix the temperature of the ionization zone. And then using the TT relation, we can add also the temperature of these other 2 zones. Then we use these 2 elements that were stable in density to fix the density. And to compute this measurement, we use the flux, putting it in PyNab. Finally, we can use our temperature and density to have our abundances in each zone.
So using PyNab, we estimated the chemical abundances, the ionic abundances of different elements in our galaxies, and we first plotted the relationship between the ratio of the ionic abundances of the nitrogen and oxygen against the oxygen abundances of our galaxies. And in order to use as a reference, we also plotted in this diagram those same values, but for different galaxies in the chaos survey, as well as using galaxies from low and high redshifts. So if we focus on those 2 stars, these mark our galaxies abundances using different ions. As we have denoted in the legend of this table, we have the nitrogen 2 and oxygen 2 ratio, and the nitrogen 3 and oxygen 3 ratio. The fact that they are so far apart could be explained by the presence of very nitrogen-rich regions in our galaxy that are very highly ionized. And the reason of this is the Wolf-Rayet stars that have such strong stellar winds that they strip out and enrich all their surroundings, which can also explain why these 2 points are so far apart from each other. We can also compare our values to the solar one, which is denoted by that little small yellow dot. We also plot our CO ratio for the ionic abundances of the carbon against oxygen. And we can see how in this case, our galaxy, which is that one, it also sits very high in relation to other galaxies with similar oxygen abundances, which can also be explained by the presence of these Wolf-Rayet stars. Finally, using our flux ratios, we can also plot a BPT diagram using and denoting the different regions that can be found in the Keeley 2001 and Kaufman 2003 papers. We can see how our galaxy comfortably sits in the star-forming regions in both cases. So these are different conclusions we arrived to, and if you have any questions, we are more than happy to answer them.
Questions? Are there any questions? So myself, I'm not familiar with PyNab. So what are the physical ingredients? Is it an optically thin model or like a cloudy-like relative transfer model?
From what I read, I think it actually solves like equilibrium equations to measure like the pop of the state, I think.
Okay. No question.
I think I just missed it. So one of your conclusions is that you got a high CO abundance. Just wondering.
It's like CO. I think it's C overall.
Okay. So
no, sorry, no.
Okay.
Yeah.
Thank you. No, just in case I had missed it somehow. Okay. So fair enough. Thank you.
Thank you. Oh, better.
For me, this all looks like a black box on the outside, but do tools like this PyNap software offer any possibility to do an error propagation of some sort?
Oh, yeah. Well, basically, for all the error propagation, we use the uncertainties package in Python and adapted many of the functions, and it basically calculates automatically all the error propagation for all the different functions. You just have to use them in combination with each other, and you can carry out your errors through the entire project. Very easy.
Okay, so thank you.
Hello, everybody. So we, Tabashi, Leo, Lily, Ziming, and Saurabh, and me, Eleonora, we looked at machine learning techniques to turn rotational lines into powerful diagnostics of physical conditions inside giant molecular clouds. And for that, we looked at the nearby giant molecular cloud, Orion B, which you can see here in the background. To set the scenes, so as we have heard in the lectures this week, molecular clouds are highly hierarchical structures with which fragments into higher density regions, the filaments and cores, where star forms. And as the most abundant molecule, the H2 cannot be observed in a submillimeter due to its homonuclear nature, we have to make use of other molecular lines and other tracers to look at the physical conditions.
So the goal of our project is to estimate the molecular gas column densities in the Orion B giant molecular cloud. And the motivation is that we hope to produce these density estimates that are more rigorous than commonly used methods currently. So super brief overview of commonly used methods. One is we often use the CO line intensities. We assume a linear relationship multiplied by a constant value, and then we get molecular gas density estimates. Or we can use dust observations, do SED fitting, which we've heard a lot about, get the extinction values, and then again multiplied by a constant and get molecular gas density values. So our aim is with random forest and principal component analysis, as well as using all the data which you'll hear about, is to provide density estimates that are more reliable.
So I will quickly describe the data. So we were provided the Orion B program data, which stands for Outstanding Radio Imaging of Orion B. So these data were acquired with the 30-meter Orion telescope at a resolution of less than 0.1 parsec and a spectral resolution of less than 0.5 kilometers per second. So we were provided like 12 spectral cubes. And with this spectral cube, we did an integration for each pixel. So we were provided this spectral. And using GILDA software, we integrated the spectra
and we computed the noise level and the peak temperature. So we have all these data, so these 12 spectra, and basically each line will probe a different density of the molecular cloud. For example, 12CO will probe the outer region, while N2H plus will probe the denser region.
So, okay. To get a first understanding of the correlations that we can find in our dataset, we applied principal component analysis, PCA for short. And what we are especially interested here is the first principal component, which gives us the direction of largest variance in our sample of 12 different integrated line intensities. So as you can see in the top plot, the first principal component is the one with the largest component. And what's interesting to note is that all of our 12 lines contribute positively to it. So this implies that there are some kind of underlying physical processes which could be similar for them. Now, to test our theory, we plotted the PC1 component against the column density of H2. And what you can nicely see here that there is in fact a trend, but it's not a linear trend, which we would like to have. Therefore, we moved on to a more sophisticated method.
Yeah, so to better predict the column density of H2, we use the random forest method. It is a supervised machine learning method that have a lot of decision tree and combine them to get the final results of the column density. And here in the left, you can see that we use the whole image that predicted from the dust as the reference, except the red square in the right of it as validation. And we use the random forest to predict the result is shown in the middle figure. And you can see that just by eye, it is quite well consistent with the reference. And if we plot the ratio in log space, you can see the ratio is quite close to 0, means we are getting a good results. And when we compare our result from the random forest with the result from the traditional CO to H2 conversion factor, we can see that our result have a much more linear relation with the reference column density. And it also have a smaller bias and smaller standard deviation.
Yeah. So after 13 days of hard work and fun time, we could conclude using the machine could predict using the random forest technique that column densities are estimated to a factor of 2 as compared to the other traditional method, XCO method, would do it by a factor of 10. So now what should we do further? The future goals can be that to prove the generosity of the machine. So for that, we need to use this machine on other nearby molecular clouds like Orion A, Taurus, and Perseus. But if it doesn't work, then we have to train the machine on them as well. And what about the other galaxies? Since these results might be, relation might be metallicity dependent, maybe we need to train the machine on other galaxies and increase the data sets. Okay, thank you. And I thank my supervisors, and yeah, thank you.
Questions? Okay. Maybe you can keep one. Oh, doesn't.
Thanks. In one of the very first figures, you showed the data or the spectra next to each other, and there was some very obvious correlated noise in all of them, some lines probably from scanning artifacts. How does the machine learning algorithm, such as the random forest, react to this kind of correlated noise? I assume it is very much poison for those, right?
Yes, so we still include noise in the random forest algorithm. The reason is for like 12 CO, it's quite strong, but for other emission lines, if we exclude the noise, then it will be a very little part that not representative for the whole data. So we still include, and as you can see in the results, it predicts pretty good.
Other questions? So you worked with the column densities, but did you have some tracers that would give you access to other parameters, density, temperature, things like that?
For the random forest?
Yeah, I mean, for any of the methods. That
Oh, yeah. So we are using all this 12 intensity as well as the 12 peak temperature. Yeah.
No more questions. That's a question. Yeah. Bye. Bye. Bye.
Actually, other principal component represent other physical properties. They probably represent other physical properties, but we don't have time to check that. Yeah.
Okay. Thank you.
Okay, the title of our project was Spreading Metals in the ISM. And so the idea of our project was that we look at a simulation from a paper by Romano et al., where they investigated whether just stellar feedback could be responsible for ejecting a majority of gas from ultra-faint dwarf galaxies, quenching the star formation early. And for that, they performed simulations with numbers where the galaxy was based on the dwarf galaxy Virtus 1, which is here shown in the beautiful image from the Stone Digital Sky Survey. And yeah, they used the box size of 2 kiloparsecs. And on the right-hand side, you can see some of the results from the simulations in the paper, where on the left-hand side, there's the density, in the middle, the temperature, and on the right-hand side, there's the metallicity, and it is shown how it evolves over time. Yeah, and the idea is that we, on the one hand, we reproduce the simulations, which we did with a lower level of detail since we are somewhat limited in our computing resources. So we use the maximum refinement level of 7 instead of 11 from the simulations, which corresponds in the paper to about 1 parsec. And we also compare the simulations for cases where the supernovae deposit different energies in the galaxies.
So the first thing that we did was to run the simulation with the same initial parameters as the reference paper to see if we could reproduce the results. We saw the results of the simulation, and we have also calculated radial profiles. You can see in the first column those for density, and in the second column those for pressure. The lines in which we are interested are the black one, which corresponds to the beginning of the simulation, and the red thick one, which corresponds to 20 megayears in the adiabatic limit. If we compare our results to those of the paper, we can see that the behavior is identical except for the level of detail because of the low resolution. In the density profile, we can see how density decreases in the innermost regions by 1 order of magnitude, more or less, and the same for the pressure, in which we can see how the hot pressurized supernova ejecta expands to the outer parts.
Okay, so now I can show you a couple of nice slices. Yeah, so the video isn't running, of course, because it's a PDF. For on the left-hand side, you can see the simulation with 10 to the power of 51 ergs. And on the right-hand side, 10 to the power of 52 ergs. And these are slices of the density. And in those, you can see that at this time point, 5.7 megayears, which is the longest time we could run the 10 to the power 51 erg simulation, because it took a quite long time because the time steps got really small. The bubble on the top is actually a bit larger than the bubble for the lower energy case. Oh, this also doesn't work. Okay, now here are slices of the metallicity, where you can see that we actually have a lot more metallicity right now in this ISM compared to the lower energy case. This is the temperature. So you can see that not only did the bubble spread further, but we also have a higher temperature, so likely also a higher pressure in this bubble, so it will extend further in the future. And the last one is just the radial velocity, where you can see the radial velocity is also a bit higher because you inject more energy. So yeah, and now Banya will tell you a bit about what he did.
Yeah. In previous part, we changed only energetic of supernova explosions. And here, instead of changing energetics, I decided a bit to change initial conditions to add rotation to our galaxy, because for now it's considered like it's stable, it's not moving, and only supernova explosions and stellar wind matter. Yeah, and it's inspired with two starburst galaxies, which is Markian 71 in NGC 2366 and this strange name, which well described in work of Penck in 2023. And here you can see that in the direction of outflow, you also see a slow increase of metallicity. And I was wondering if we can reproduce this with almost the same setup, this increase for observations, and if it will be the same. So yeah, this is Markian 71 in 2366. It published recently, so you can look. And his initial conditions for potential and density. I also did very dumb assumption for pressure, and the velocity comes from potential. And after a bit of computations and help of ChatGPT and some amazing supervisors, Simon, Eva, and Donatella, I was able to compute initial conditions, but afterwards everything exploded because it's pretty difficult and not very straightforward how to stabilize rotating disk. So yeah, that's my results.
Okay. Few questions?
Yeah, and thank you for your attention in every language.
How much time, what is the size of your simulations in pixels, and how much time does it take? Did you do it on your laptop?
Yes, and the maximum size is 2 in power of 7, so it's 4,000 something.
And how long does it take, the simulation?
On my laptop, it took 3 hours on 22 cores for initial condition, which is not changing, and I'm not sure what was about supernova sponge with increased energy.
Have you idea? Okay, we didn't estimate time.
Yeah, thanks. I was curious about what is the assumption you made to try to find an equilibrium solution for that Miyamoto Nagai disk? What was the principle behind your equilibrium solution?
Well, I assumed that there is a long work around this field, and they made analytical solution for this profile. And what left for me is calculate mass and velocity, which is comes from mass, so very easy equation. And then I assumed thermal isothermal disk, but for some reason it doesn't work. Maybe there's some bugs. So yeah, one version of bugs when I computed mass in wrong way, and this is my best results. I have no idea what bugs there for now, and I'm going to investigate it a bit more.
Okay, any more questions? No. Okay, so thank you.
So we are project 8. So we are working on JWST galactic spectral SEDs, and we are trying to fitting them using Beagle. So to be even more clear, so this is an example of galactic spectra. So it's one from Beagle, and it's z equals 0. So that's why you have a part of it which is in UV and the other part which is in visible. Some interesting things on that. First is that the break is not at the Lyman break, but at the Lyman alpha. But this other break is on the break. And you have also a few interesting lines, H beta, O3, and H alpha. So those are the interesting lines because those are intense. And so in our case, we are trying to see some galaxies which are redshift. And so this is why you have the redshift on the y-axis. And you can see that those lines are going to the infrared, and you have above the filters from JWST. So you can see why we are using JWST just because of the redshift. And you have all the stuff I mentioned, which are highlights. And to be slightly more precise, it's not like random JWST data. We are looking at JADES. So it's one of the largest surveys from JWST. It's almost 1,000 hours of photometry and spectroscopy. And we also use a part of CONDELS, which is HST data.
Yeah, and so kind of just briefly about the SED fitting procedure we took. So we first curated a sample, collected the HST and JWST photometry that is a part of JADES, and that is something that we input into Beagle along with inputs of the star formation history, nebular gas, and dust, which we use relatively uninformative priors for. This all goes into Beagle, which is a Bayesian analysis SED fitting code. And what we're able to output is the same input parameters, but with statistical constraints. And we're able to get mock spectral templates that were fit to the photometry data after it was convolved. So to be a little more specific about the selection that we used, we were trying to select for extreme O3 H beta emitters. And so in particular, we were looking at things with H beta O3 equivalent widths greater than 200 angstroms. And so we used 4 JADES filters to make our selection. And this gave us 30 galaxies in 2 redshift bins where in our lower redshift bin, we had an average or a median O3 H beta equivalent width of about 300 angstroms, and in the higher redshift bin, 16 galaxies with a median equivalent width of 470 angstroms. So you'll note that our higher Z bin has on average higher equivalent width in these lines. And so these are kind of just a few examples in each at each redshift range of some of the fits that we got out. And overall, we find that there's a larger variety in the fits that Beagle gets in our lower redshift bins. So you'll see that across the whole sample, there's some potential Balmer jumps in the most extreme O3 H beta emitters. And in our lower redshift bin, we get a variety of things like Balmer breaks and dusty galaxies. So yeah.
Hi, everyone. Okay, so I'll just talk you a little bit about how to use results from Beagle to infer the properties of the galaxies in our sample. First of all, as Zoraida has just said, we are selecting the most extreme galaxies in our catalog. So one may wonder, are they all AGN? That's why we took the masses and emission lines from Beagle to build a mass excitation diagram. And as you can see, our data, so the yellow hexagon in these plots, lie all below the demarcation line between AGN and star-forming galaxies. In addition, their equivalent width are consistent with the trend observed in other extreme star-forming galaxies at high redshift. So we are considering starburst galaxies with extreme conditions. And such conditions reflect in highly ionized systems. In the plot on the left, yes, we reported how the gas phase metallicity from Beagle varies with the ionization parameter. So as you can see, our samples exhibit on average a low metallicity and very high ionization parameter. And just as a reminder, the ionization parameter tells you the number of photons ionizing hydrogen per hydrogen atom. So these are really ionized systems, but are also very efficient ionizers as parameterized by psi ion. So in the plot on the left, you can see that all our sample is offset from the average value of psi ion. And this means that these extreme free emitters are indeed a great laboratory for studying, for example, reionization or more in general, Lyman continuum emitting escape.
Okay, we'll be discussing the mass metallicity relation. This is the nebular metallicity in relation to the stellar mass, and we can also see the error bars. And also we compared our samples with other study previously, not sorry for not mentioning in the reference here, but this is someone else's work from previous study with similar redshift with our sample. And here is, we can see from this small circle that our metallicity is in line with this previous study. And this is the gas phase metallicity in relation to stellar mass.
Okay, we focused on around the redshift is 3 or 6, but we also have some result for the redshift 8.3. I show the data from HST and the JWST data, but actually this galaxy is observed by ALMA, but the Beagle cannot use it, so we didn't use ALMA data actually. Yeah, this is a really high redshift, so the 500 mega year baby galaxy, and it's composed of 3 big clumps. Yes, here I show the SED or best fitting. So yeah, in general we can see strong emission, so we can consider or interpret this galaxy have a high star formation rate and highly ionized. And we can also see the strong free bound continuum emission. So it shows we can interpret there's a hot stars and emit enough ionizing photons. And my last slide is this. By using Beagle, we can know a lot of physical parameters. For example, there's a stellar mass. Yeah, we can see it's small mass, but actually we didn't use ARIMA data, so maybe it can be underestimated. And it also shows star formation rate, optical depth, and the ionization parameter. And yeah, as a result, this shows it's a really strong star formation galaxy. Yeah, we don't have actually conclusion slide. That's all. Thank you.
Thank you. Questions? Oops. Oops, pardon.
I have a question about extreme O3 galaxies. Do they reach theoretical limit of excitation for O3 per H beta ratio?
Can you repeat the question again?
Do O3 emitters reach the limit of theoretical O3 per H beta ratio?
I mean, their ratio is consistent, for example, with the local higher Z analogs. So it's not like, I mean, it's not like the most.
Yeah. But when you see on BPT diagram, there is a upper limit which O3 per H beta ratio can reach, and there is
Okay.
On the right hand, you also have S2 per H alpha ratio, where we consider that it's already not photoionized, but shock ionized. So I'm wondering if we can say something about these systems, for example, to say that it's already not case B ionization, but something else, because they above this limit.
Okay, I didn't consider the BPT diagram, but rather the mass excitation diagram. Anyway, the demarcation line in the mass excitation diagram is similar to those obtained in the BPT. And if you remember the plot I showed, our galaxies lie like very close to the demarcation line. So yeah, very close to the limit for starburst galaxies.
Okay, I see. Thank you.
And I don't know for the shocks, but we can talk about later.
Do you consider radiation from binary stars in Beagle?
I don't think that. Oh, wait. No, Beagle does not use.
And do you think it may explain why you have more ionization?
Yeah. So binary stars would contribute to that. Yeah.
Even at these ages, you think it will play a role? Okay. Okay. So thank you.
All right, thank you. So we are Project 9, if you were still awake. So there's us and one more to go. You're doing great. So we were numerical simulations using Ramsey's and Arabo codes. These are both of the codes that Simon presented in his lecture. So you might have to think back a little bit. So this is NGC 628. This is probably a JWST image that you've seen many times by now. If not, now you have. This image is really exciting because it's really introduced extra research into shocks, because as you can see, there's a lot of bubbles in this image, and we added one more. But these are really important, as we've discussed in the lectures, to the ISM. So hopefully I don't have to convince you on that. So what we actually did for our project is, after understanding that this is something we wanted to work on, we split into 2 different methods. Part of our group worked on developing actual simulations using Ramsey's of different shocks driven by supernovae. And the rest of our group worked on data processing using already run simulations from a repo. We used one snapshot.
Thanks. I want to give you a bit of a background of what to expect when you look at our simulations. What we try to simulate and look at is mostly supernovae shocks. And for our purposes, this is mainly an enormous injection of pressure at one point in our space. And what happens is that all the material will be pushed outwards at enormous speeds, initially so fast that the motion is ballistic and not well described by hydrodynamics, and very fast. And then after a short while, when hydrodynamics is a good description again, you will end up with an inner region where everything is very supersonic and an outer region where it's still subsonic. And you can look for solutions to the hydrodynamical equations. You will find that you will have solutions that are always subsonic. You will have solutions that are always supersonic. But you will have no solutions that can be both supersonic everywhere outside and inside and subsonic outside. So what we will end up with is a shock, a discontinuity. You will find no continuous solutions. And you can find out some of the properties of this shock by a very simple estimation. If you look at the continuity equation here in the shock rest frame, so where the shock is at rest. So all your time derivatives vanish. So the continuity equation reduces to this very simple form of the conservation of mass. And if you have a post medium, an outside medium that is much more dense than what is inside, so everything has expanded already, then you can reorder this equation and you will find that the post velocity after the shock has passed through is much smaller than the pre-shock velocity. And now note this is in relation to the shock rest frame. So what has been shocked moves along with the shock, is what this is saying in other words. So if I put this into maybe more understandable sentences, the flow is compressed and slowed down in the shock rest frame. And what the shock does, it is converts bulk kinetic energy into heat.
So to model those supernova bubbles, we relied on the Ramses code, as we said before. So here are some technicalities about the Ramses code, but what you have to keep in mind is that it uses a Eulerian approach, and it's really great using the adaptive mesh refinement, as we can see here. So it's really great for multi-scale resolution and which are involved everywhere. And so if you have a question to discuss with Man and see his lecture. So we used the Ramses to first on really simple 1D and 3D models, not a really straightforward simulation to do, but we used that and then we created our own input file in order to create our own set of instability. Yeah.
Okay, so we had some nice movies, but sadly this is a PDF. First of all, we have a simulation of a very normal supernova with 1 times 10 to the 51 ergs. The surrounding medium is 100 helium, or like a hydrogen per cubic centimeter, and the initial pressure inside. So the initial setup is we have an over-pressurized region of 0.55 parsecs with a high pressure of the supernova, and then it expands. And as you can see here, like the top, so top left is pressure, bottom left is density, and top right is the pressure profile on one axis, and down right is the density profile. And as you can see, the density has a spike there, it's a shell, and same in the pressure, where you have like this continuity. Then if we plot okay. So if you take the measure from here to here, how big is it? That is like the shell radius. And if we plot the shell radius over time, then we get this, where the blue line is the theoretical. Does it work? No. Yes, now it works. And the red lines is the end of the set of Taylor phase, which is like the thing we are kind of simulating. And as you can see, there's a quite good approximation And yeah, so that kind of works. Then we have the same thing with with the energy of 100 supernovas. And here on the right-hand side, you can see the result. Yeah, and they are pretty much similar, not much going on. However, we have a third simulation. This has a magnetic field.
Okay, I'm sorry. So maybe this one.
So yeah, this simulation has a magnetic field of arbitrary strength because I couldn't figure out the units. And as you can see, this actually kind of differs in the profile and also like in the shape of the whole supernova. And so basically what's going on, like it easier expands along the field lines and it's getting suppressed perpendicular to the field lines. And we can also see that in this plot. So where like the red, like the green points are like along one axis and the yellow points are along the other axis. As you can see, it's no longer spherical and instead it's getting ellipsoid. Yeah, okay.
Okay, I'm going to run through this second part really quick. But the second part of our project is we've built our own bubble finding algorithm for this Arecibo snapshot. So we need to be a chef and slice our galaxy snapshot into cubes, and then we can search each cubes for a minimum density. We know the inside of a bubble is a hot, very low density volume filling component. So we're going to select that least density, find the coordinates of these particles, and this is the center of our bubble finder. So then once we actually have a bubble, this was our best example. So of course we're showing it to you. We compute all of the properties in different shells to see how that changes with radius. This is the actual size compared to the galaxy. So it looks large, but remember how small this is on the grand scheme of things. So we can see density and thermal pressure increase with radius, as we would expect for one of these bubbles. And radial velocity increases until we get to shells that are outside of that dense shell.
To finish it off, we'll look at what went wrong. So we first use that the radial velocity to determine what is the size of a bubble and establish the radius, and then run this algorithm over the entire volume, and we find like 15-ish potential bubbles. Some of them are kind of like bubbles, but we could not verify them all. But most of them are not bubbles. So this is because outside the volume, we are not very sure of the spherical geometry, because as the bubble expands, and we saw in the previous lecture this morning, they don't really stay spherical. And also, these supernovae are not really isolated like we did in the Ramses simulations. Yeah, things can go wrong. And this is one of the big failures that we had, where we classify this as a bubble, but it's not really a bubble. So I guess that is it. Any questions? We're happy to address them. Thank you.
I think that's an exactly.
Nice speed run.
Is the size of the Arepo simulation big or is it small? Does it fit in a computer? No, no. Does it fit in the computer?
Yes. Each snapshot is around like 2.5 to 3 gigabytes. So we could barely run them on our computers. Mm-hmm. So that is why we were not able to do like a very refined integral. That's why we also have like a resolution limit to what size of bubbles we can find, because our shells were 75 parsecs, which is fairly large.
Do you see bubbles? Do you see shocks in all the bubbles?
We did not really do like a line profile to find the discontinuity, because if we go back to this method, we are basically integrating over the shells to find out the density, and that shell is 75 parsecs. And if you were to do that at the shock front, you would smoothen it out. So you would basically see something that goes like this, not really that. Yeah, it's just we'll need finer shells. And also we didn't have enough particles within this region to be able to resolve this structure because it's quite small.
Can you identify shocks with velocity field?
Can you
Then?
repeat?
Can you identify shocks with velocities then?
With velocities, partly yes, because we expect, because this is an outflowing gas, which is very hot inside, we expect the radial velocity to be positive inside the bubble. And as soon as we get out, the ISM is doing its own thing. It doesn't really know about this bubble. So the radial velocity should like immediately die off after we go out. Like once the shell is outside the sphere. Yeah. So that was the reliable measure that we used. But we could, in principle, use the density or the temperature profiles or something else. We did not try those.
Okay, I see. Thank you.
Oh, wait, we did try density. It didn't work well. We did try density. Okay.
Okay, thank you.
Hello, everyone. We are Group 10, and we present our hands-on project, how to interpret molecular lines from dense gas in galaxies. Our motivation was to understand the physical conditions of molecular gas in a nearby galaxy, namely NGC 1068, by analyzing two transitions of CO emission. We aim to derive key physical parameters such as gas temperature and column density in regions affected by both star formation and AGN activity. For this, we used the local thermodynamic equilibrium methods, like rotational diagrams, to determine the gas temperature and the column density. And then we linked the observational results to chemical evolution with the astrochemical modeling code, USC-CHEM, to explore how the gas abundance gets affected by these parameters, like density, radiation field, cosmic ray ionization rate, and temperature. Yes, and we determined the values of these parameters that give rise to the observed column densities of CO in this galaxy. So a few words about carbon monoxide. This is the second most abundant molecule in the universe, mainly used to trace molecular gas in the universe. Its rotational transitions from 1 to 0 through 6 to 5 is accessible in ALMA bands 3 to 9. And from its from the CO line intensity, the XCO, the conversion factor can be calculated, which can be used to derive the molecular hydrogen column density. We used ALMA data of NGC 1068. It's a CFR2 active galaxy at a distance of 14.4 megaparsec. And we used the observations of its circumnuclear disk. Here we show the moment zero map of the CO, one of the CO transitions. From this, we chose two regions that are denoted by these green circles. And in these green circles, both of the spectra in these two transitions are shown that from which we derived the line integrals by Gaussian fitting, by fitting a single line. And we analyzed this data with the equation above. From this, we derived the column density and the temperature. At the first step, we used this W parameter, that is the line integral, and approximated this. So we used this equation as if it was a linear equation. And in this, the logarithmic part of the right side of the equation was the intercept of this linear equation. T was the parameter that we were looking for, and the left side was the function itself. From this, we had to only use the gamma U constant and the GU, the degeneracy. The N was the column density, and Z is the partition function. EU is the upper level energy. And from this, we could plot these rotational diagrams seen here. These are from the two regions chosen, and the two blue dots are for the CO transitions. And the fit itself, the linear fit itself, is the temperature. It's important to note here that, of course, two lines can always be fit with a linear fit, but we consulted the literature and we confirmed that we could use the LTE approximations here, so it was an assumption that we could use in this case. So after that, we only needed to calculate the partition function. Then we could derive the column density from the equation above.
So we're going to use the chemical model, which is called UCL-Chem, and it's a time-dependent gas-grain chemical code. It has different modules for different environments, such as molecular clouds, hot cores, and C. And it enables the user to change the physical conditions. And combined with a chemical database, such as KITA, we are able to simultaneously treat gas phase reactions and grain surface chemistry, whether in 0D or in 1D. So we have also the addition of a spatial component. So the first thing that we wanted to check is the effect of these different physical parameters on the output of this data. So first of all, we ran the model with these different set of fixed values for the parameters. And we got an input, which is the fractional abundance of CO with respect to H2. If you can see here, the plots, we have the solid lines, which denote the gas phase CO, and the dotted lines that denote the ice phase. And what we did is that we changed these parameters one by one in order to see its effect on the outputs. So we changed the density, the temperature, the cosmic ray ionization rate, and the radiation field. We can see that the density is the parameters that affects the most these outputs. And it is noticeable that the radiation field, which is the last plot, does not affect it that much. And this is quite expected because you're working on a media with relatively high visual extinction. And so the UV cannot even penetrate, so it gets attenuated quite fast at the edges. The second thing that is interesting with this code is that it enables us to trace the major reactions routes that involves the production and the destruction of CO. And we see the production of CO is majorly affected by the reaction of H and HCO on the surface of the ice mantle, which is the formation of CO. And destruction of CO comes from mostly its reaction with H3. But again, this is just at one timestamp, and these reaction rates evolve with time. And on the left plot, we see the different species evolution with time that play a role in these reactions. Also, one more thing in the previous plots is that we see that the general trend is that the CO is down, however, the ice phase goes up, and this can be partly attributed to the freeze out of CO on top of the ice mantles. And finally, we wanted to match the observations to the chemical model. And since we're in an optically thin environment, we can do the approximation of transforming the fractional abundance, which is the output of the code, into column density. To do so, we multiply this fractional abundance by the AV times 10 to the power 21, which is the one magnitude. The AV is calculated in a crude way, just for SPF hydrogen, which is the input of So we get the evolution of the column density of CO with respect to time. And by combining it with the column density that we got from the observations, which is 510 to the 18, we can have a very crude estimate on the age of this cloud, 10 to the power 5. Finally, we did a lot of assumptions in this project. So LTE and stuff. So there's a little room to error propagation. We did at least there's a new error that adds on, which should be considered. We could have also used other CO transitions to have a better fit. And we could also say Galaxy. I'll leave you with the conclusion and thank you for your attention.
Questions? So all this surface chemistry depends a lot on the accumulated surface of the grains and the freezing of molecule and so on. So have you played on the size distribution or is it something fixed?
The size distribution of the grains?
Yes. Okay. Questions? No more questions. Okay, so thank you.